Good morning, ladies and gentlemen. My name is Jouni Envall, and I'm here to talk about the CubeSat missions and payloads related to electric solar wind sail and its tether payloads. Here's a rough outline of what I'm about to say. I must start with a question. Electric solar wind sail or E-sail. Please raise your hand if this is the first time you hear about this topic. I see no hands here. Excellent. So that means I don't have to spend too much time on some of the early slides here. So anyways, I'm going to say a couple of basic things about E-sail, something about missions that it enables or will enable. Then a little bit about the CubeSat payloads thus far and in the future. I may also talk about some our current novel tether production facility. And at the end, let's see if we have some conclusions. So everybody knows E-sail, I see. So this is familiar stuff, I suppose. In any case, it is a propulsion innovation made at our institute. It is based on tapping the momentum of solar wind with long conductive electrically charged tethers. The number of tethers can be anything starting from 1. And this kind of sort of a baseline concept that I show here is the one which has 100 tethers, each 20 kilometers long, charged with 20 kilovolt voltage. And with such structure, one would get roughly 1 Newton of thrust at 1 AU distance. 1 Newton is actually quite a lot when we're talking about a propulsion system, which doesn't require any propellant other than solar wind, of course, but no propellant that we would have to carry with us to the mission orbit. Some interesting numbers there. One thing worth noticing is that the thrust scales down as 1 over r instead of 1 over r squared, as it does with conventional solar sail or photon sail, which is an advantage to this propulsion method. So we get the thrust from solar wind, which blows outwards from the sun. So of course it's natural to think first about missions going outwards in the solar system or even to interstellar space. But it's actually possible to maneuver with such a sail within the solar system back and forth. And especially nowadays, we've been very much interested in touring missions, for example, within the asteroid belt, whose outcome might be scientific or commercial, the latter one being related to asteroid mining of minerals or water ice for rocket fuel manufacturer in orbit. There is a very fascinating concept of a multi-asteroid touring mission with up to 50 CubeSats. And I will not go very much into details about that. You see a couple of pictures, but you will hear a lot more about this in the very next presentation given by that. So I will move forward here. So typically, what we do, what we have done, and what we are still about to do during the next missions with CubeSats is that we have the typical CubeSat 1 to 3 units. We have 1 tether on board for simplicity. The length of the tether being some tens or some hundreds of meters, and voltage in the range of 1 kilovolt, either positive or negative. You will see details in upcoming slides. So far, we have been we have remained at low Earth orbit. So of course, being inside of the magnetosphere, we're not dealing with solar wind instead we can do similar testing of this concept when the satellite is flying with its orbital speed through the ionosphere quadrant. And the typical mission objectives have been and will be first of all to deploy the tether. So yeah, perhaps I didn't mention it with the first slide, but in order to keep this sail open, it has to spin. So it is the centrifugal force that keeps the tethers spread. So when you have a CubeSat with one tether on board, what you do is you first have to spin the satellite, and then you have to reel out the tether. And at the end of the tether, there is a tip mass weighing 1 gram, 2 grams to assist. And once you have deployed the tether, then we try to observe the E-sail force or the Coulomb drag force with some suitable method. And now this is not straightforward because with these tethers of this length, and only if you have a single tether, the forces we're talking about are in the micronewton range. So observing them directly would be very, very difficult. So what we need to do is we need to find a suitable way so that we can observe an effect that accumulates over time. This is the way we have been planning to do it. So when the satellite is spinning here on this picture, so the spin plane is the plane of the slide, and it's spinning here clockwise, and its orbital speed is upwards. So now if we put the voltage on, then on the left semicircle, so the E-sail force now is always downwards. It's against the speed vector. So basically now, if the voltage is on, then on the left semicircle, it would the spin rate would be going down, and because it's going upstream. And on the right semicircle, the spin rate would be going up. And if we kept the voltage on constantly, then these two would cancel out. But if we do it in a synchronized way, so that we only keep the voltage on during the left semicircle and off during the right semicircle, then our spin rate will gradually start going down, and vice versa. So then a few words about E-sail tether CubeSats that have flown. The very first one was the Estonian 1U CubeSat, ESTCube-1, which was launched in May 2013. It had one tether, 16 meters length, which would have been charged with 500 volts voltage, either positive or negative, and for the positive mode to operate, it had two cold gathered electron guns. Unfortunately, the mission was not successful. Our mission, I mean, the satellite performed fine, but our tether payload unfortunately did not. So instead, in fact, we couldn't get the tether out because the relay system jammed. The next launch was the Finnish 3U CubeSat, which was launched last summer. Slightly bigger in every way. The satellite was slightly bigger. Our tether was somewhat longer, 100 meters. The voltage had been scaled up 1 kilovolt plus or minus, and also the number of electron guns was 4. As you can see, we have not yet started the mission. First of all, unlike in ESTCube-1, in Aalto-1 we are not the only payload, so we've had to wait for a turn, and also the satellite has experienced and is still experiencing some problems with its attitude control. And as you saw from the earlier slides, our mission leaves lives or dies with attitude control. However, things have been starting to look a little bit brighter during the spring, and if we are lucky, we will start getting something, perhaps even during the summer months, but we'll have to see. Then a few words about the tether. So, as you already saw, the tethers, they have to be, first of all, conducting. Then, of course, they need to be strong enough to survive mechanically. They have certain thermal characteristics. They shouldn't weigh too much and so forth. And the one thing that I have written with a bold font is that the tether needs to be constructed of several wires. So a single wire would not suffice, because if you reel out a long single wire during a space mission, it won't live long because of the micrometeoroid bombardment. So instead, we need to have some structure, some multi-filament structure to have resistance against micrometeoroids. And several geometries have been suggested. Some have been, many have been studied, and some have been manufactured. The current one that we are now actually building at our own laboratory looks like this. It's a ladder shape with parallel wires, which, well, number of them can be anything starting from 2, and then these perpendicular wires. And this shape has, or this geometry has not been selected for it, so it's not optimized for its performance during the mission. It's optimized its performance during development at this point. And at this point, I can't say too much about the materials, and also I won't go into details about the technique itself. Here are a few photographs of our current setup, which is in test phase. So on the left hand, on the picture on the left hand side, here on the bottom you see 2 parallel wires going over the bonding plates, and then the picture on the bottom right corner, you can actually see those 2 parallel wires going from left to right, and one perpendicular wire going from bottom to up. Also, there is seems like there's a third parallel wire in the middle, but that's actually a reflection of the edge of the last bonding plate. So much about the tether at this point. I hope I can talk more about it in some future workshops. But then something about our next mission ideas. So you saw ESTCube-1 and ESTCube-2 and 3 are currently in planning and early development phase. So why we are doing, so we are of course once again making cooperation with Estonians with their student team, and why we are simultaneously or semi-simultaneously building ESTCubes 2 and 3 is that the next big goal is ESTCube-3, which is supposed to be the first one to reach solar orbits. So to go outside of the magnetosphere. And as you can see, we have not selected orbits. So at this point, we try to design the satellite in such way that it could perform in multiple optional orbits to wherever we get a decent launch opportunity. Lunar orbit has been suggested as well as Lagrange points. So then the role of ESTCube-2 is to be sort of pretest mission for ESTCube-3, so it would still go to the lower orbit to test some of the key technologies of ESTCube-3, especially the cold gas thrusters, which are needed for the spin. And also, any mission with tether payloads at the moment, also the lower orbit is valuable. We need all data which we can get, so it also serves as kind of a redundancy for that purpose. And I mentioned here briefly the plasma brake concept. So in fact, this Coulomb drag force or E-sail force, it has there are basically two ways you can utilize it, either for propulsion or for atmospheric re-entry lower orbit. But I won't go into the latter one because that's outside of the code in this workshop. So the tether length would be 300 meters, and it could be charged up to 6 kilovolts. Here are a few CAD pictures of the payload with the key components marked, tether reel, tip mass, launch locks, etc. Here is preliminary mass estimate, so we try to remain below 600 grams. This picture, actually, the perspective is a little bit misleading. It's actually about half unit in size. And also here on the right, you see a fairly recent CAD drawing of ESTCube-2, and at this end you can actually see our tip mass. Yes, and my final slide. So the test missions of E-sail hardware have already begun in 2013, but we're still waiting for proper results from orbit, and if we're lucky, we will start getting them pretty soon. And we are already making the next ones, especially you should remember ESTCube-3, which if things go as planned, then it could be the first spacecraft to test the use of solar wind for spacecraft.
Any questions?
Thank you for the presentation. A short question, maybe you said, and I missed it, for Aalto. You said 1,000 volts, I believe. What kind of current are you drawing? What is the power requirement for your experiment?
The currents are small. They are, if I remember correctly, they are in the range of 100 microamps or so. So basically, it need why we need the electron guns, for example, it is to remain the voltage, to keep the voltage on the tether, because of course when we charge the tether in plasma environment, the plasma basically tries to neutralize it. And so we need to be, if we have a positive voltage, so the tether would be gathering electrons from the plasma, and we need the electron guns to shoot them away. So that is what and the plasma environment, at least in all the ones case, would suggest currents of tens or hundreds of microamps.
Any other questions?
Just wondering if you have some kind of estimate of how far away how far away from the sun a CubeSat will be able to use a system like this.
I think that's more of a question of how far CubeSats can go anyways. So the one nice thing about E-sail as a concept is actually the bullet on the bottom. So of course when we go further away from the sun, the solar radiation drops at 1 over squared. So that's how much we can get power to the solar panels. However, because of the same spherical symmetry, the power consumption of E-sail also drops down as 1 over squared. So this cancels out. So E-sail as such doesn't really introduce any showstoppers there. Of course, it makes certain things harder, but I would say that to answer your question, it's more about how far CubeSats can go at this point.
And yeah, one more question.
Hi. So how difficult would it be to maneuver with this kind of system, like orbit insertion or operations like this? Would it be complicated because it's basically spinning, you have a tether.
Yeah.
How difficult would it be?
First of all, you will probably hear something about it in the next presentation. As Jaroslav is speaking about the asteroid mission. I'm not an expert on this, but there are papers that our team has published. So if you just Google our electrical cell, you should find our website, and in the downloads section you can download most of the papers as PDF. So basically, what you do is well, as with any sail, you tilt it. So you're on some orbit around the sun, and so the orientation of the sail decides whether you're accelerating or decelerating.
Okay. So just one short question to that. Can you control those wires independently?
Yes.
Okay, thank you very much.